Hello class, welcome to another video for this course. In this video, we are going to start third section of chapter 4, section 4.3, and introduce logarithmic function. So we first introduce the logarithmic function, and then we will see examples, and also we go over some of the properties of this specific function. Okay, so let's start by the first example of the textbook. In this scenario, the textbooks describe that a population of 50 flies is expected to double every week, leading to a function of this format. So what is this format? 50 times 2 to the power of x. We learned that this is an exponential function. The format is the format of exponential function, where in this case, x represents the number of weeks that have passed. And so let's say 50 flies is the initial population, initial value, and then the population grows, but by what factor? Doubling every week. For that reason, this is the function of this function models this scenario. Now, suppose the question is, when will this population reach 500 flies? So let me summarize this scenario here. So in here, we are looking at the initial value, the initial population is 50. And then the growth factor is 2. Why? Because the population doubles every week. So for that reason, the equation of this function is, it starts with 50, and then the population grows by becoming double every week. So 2 to the x. What is x in this case? X is the number of weeks that passes from the initial time. So it's the number of weeks passes the initial process. So you already learned that this is an exponential function. And the question is, when the population reach 500, so when f of x becomes 500, that's the question. When the population reach the 500 flies. So that means the question is that for what x value, or after how many weeks, after how many weeks the population reach 500. That's the question. So number of weeks is x, represented by x. So the question is that for what x value, after how many weeks, what is the x value when the population f of x is 500? So if you just substitute that into the equation of this function, so the question becomes, okay, so if f of x, look, f of x has this equation. And the question is that when is the time, for what x value, the output becomes, the population becomes 500. So then we need to solve this equation. Okay, so the first thing to solve this equation for x, so we need to solve this for x, right? We need to solve this equation for x. So the first thing to do, we learned from algebra that we can simplify it. We can divide both sides by 100. And if you do that, if you divide both sides by 100, here you get 10, Here you get 5. Oh, you can actually divide both sides by 50. Yeah, you can actually divide both sides by 50. And if you do that, look, so 500 divided by 50 gives you the 10. So this becomes 10. 50 divided by 50 is 1. 1 times, so this is 1 times 2 to the x, right? So then we end up by this equation, right? And we still need to solve this. So we simplify this equation and we reach to this step. Now we still need to solve it for x. But look at the format of this equation. X, what is the role of x? X here is an exponent. So we are ended with solving an equation that solving the equation for a variable. That variable is an exponent. We haven't learned how to solve equations like this. So by the techniques that we have learned so far, we are not able to simplify further or do something now to say, okay, this is the way and this is the x. For that reason, we need to introduce something new. So we need to introduce something that we would be able to solve an equation that contains exponential component. So let's think about this question. So the question is, so now what is the question at this step? The question is, for what x value 2 to the x gives us 10? That's the question. At this, so we simplified our original equation and we reached to this step. What is the x value? What value you can substitute for the x in this equation, 2 to the x, that gives you 10? So let's look at the graph of 2 to the x, because 2 to the x is an exponential function, and we already learned about exponential function in previous sections. So let's draw the graph of 2 to the x. So that's my goal here. I'm gonna draw the curve, the graph for 2 to the x, and see if we can guess something about x. Okay, so we know that when you put 0, 2 to 0 gives us 1. So at 0, we have 1, right? And then 2 to the 1 gives us 2. So at 1, the function for input value 1, the output is 2. What else? We can try it for 2. Okay, so if you substitute 2 for x, 2 to the 4 or 2 squared gives us 4. So at 2, for the input value 2, the output is 1, 2, 3, 4, 4, right? So this is another point for the graph. What about 3? So 2 to the power of 3 gives me 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So that's gonna be somewhere here, right? Let's try one more. What about 4? When the input value is 4, when the input value is 4, 2 to the power of 4 is 16. So it's gonna be up here, 16, okay. Okay, I may erase some stuff here because I want to have a better picture. I want to have a clear picture, right? Okay, so now let's connect these points to draw the curve. So when you connect them, maybe I take this down. So when you connect these points, oops. And then you can, you know how the exponential, how is the graph of exponential function. So from the left side, they approach the x-axis, and then from the right side, they go to infinity, right? So this is the graph of 2 to the x, right? Okay, so let's look at the question. What was the question? For what x value 2 to the x is 10? So where is 10? 10 is somewhere here. Let me make my graph better. So 10, oh, and this is 16. So 10 is somewhere here. 10 is almost here, right? So the question is, for what input value, okay, the output is 10. So for what x value, so I can graphically, I can see that that x value is somewhere here, you see? So that x value is somewhere here. I can see that that x value must be a value between 3 and 4. Why? Because when you do 2 to the power of 3, that gives you 8. 2 to the power of 4, that gives you 16, and 10 is located between 8 and 16. So because the function is growing, the function is increasing, so that means my x value must be something between 3 and 4. Okay, so graphically, I can say that, okay, the answer here is a value between 3 and 4. So it must be 3 point something. But what is the exact value? Okay, so from graph, we can observe that the answer, the x value, is something between 3 and 4. So if the so to answer this question, that like the original question is that after how many weeks we reach the population of 500, I know that it's somewhere between 3 to 4 weeks, but what is the exact answer? So you see, even though if we use the graph, we still have an estimation of the x value. We don't have the exact answer, exact value for the answer. So we hit the wall at this point. We hit the ball, we have an estimation, but we don't have the exact answer, exact value for the answer. So because of that, we need to introduce something that helps us to answer equations like this, that helps us to answer questions like this, questions that involve solving exponential equation. Okay, so what to do? Think about this question one more time. We know that in this function, the function 2 to the x, we are looking for the input value, right? The question is, what is the input value when the output is 10, right? So think about function. Just recall the definition of function in general. When we have a function, right? So the question is, what is the input value that gives you 10? And we know that this function is 2 to the x, to the operation of this function is 2 to the x, meaning that whatever is the input value, the function, take that input value and calculate 2 to the power of that input value. Now the question is that for what input value 2 to the x returns me 10? So remember, whenever we had in chapter 1, when we had a question like this, for questions like this, we introduce the inverse function. And here we are able to introduce, to go for inverse function, because the original function is 1-to-1, because our 2 to the x is a 1-to-1 curve. So we are able to use the inverse function. So let's inverse this. Suppose we have the inverse of this function, then recall what was inverse. Inverse take the output value. So in this case, it takes 10 and it should returns us the input value of x. So if we can define, if we have the inverse function, then the inverse function gives us the answer, because it takes the 10, the output 10, and it returns us the original input value. So for that reason, we need to define the inverse function of exponential function, okay? So this is an exponential function. And you see the need to define specifically its inverse function. And the inverse function is called logarithmic functions. So in nature, what is the logarithmic function? It's just the inverse of exponential function. We give it this name. So in fact, we want to define a category, a family of function, which they came from as being the inverse of exponential function. Notationally, we use this notation. Let me use starting the notation. We use this notation, LOG. So log, maybe I start writing in printed format. So log or LOG stands for logarithmic function. So this is the notation of the function and what it does. Okay, let me show you what it does. So it takes the output, it takes the output of the exponential function, which is in this case 10. It takes 10 and it also take the logarithm to the base of the exponential function. What is the base here? The base is 2. You see, in the exponential function, the base is 2. So it takes 10 and it calculates the logarithm of 10 to the base of 2 and it returns you x. So that's a logarithmic function. Again, what is the logarithmic function? Logarithmic function is just an inverse of an exponential function. And we use this notation. So let's say whatever is the base of that exponential function, the logarithmic function also has that base, the same base. It's just, it switched the place of input and output. It takes to the output and it returns you the exponent. So that's the definition of logarithmic function. Okay, so we have the logarithmic function. We use this notation. We write log of x to the base of b. So this index here, b, stands for the base, which this b is the same as the gross factor, the b to the x. So when you have the exponential function, whatever is that base, it's the same base in the logarithmic function. So let me show you a couple of more examples so that you get a little familiar with this idea and also with the notation. So let's look at first example. Okay. Example 1. Example 1 of the textbook. So the question is, write the exponential equation as logarithmic equation. So for now, we just want to practice playing with exponential and logarithmic expression. So 2 cubed is 8. Okay, 2 cubed is 8. So this is exponential, right? So now look, what does this mean in terms of function? In terms of function, right? Function, it takes, this is 2 to the x, right? It takes 3 It calculates 2 to the power of 3 and it returns you 8. So what should be the inverse? The inverse should take 8, returns you 3, right? That is the job of an inverse function. It should take the output, returns you the input. So now in terms of notation, we know that this must be logarithm having the same base. What is the base in the exponential function? 2. So here also the base must be 2, right? And it should take the input value. So I should have log of, maybe I use printed for the beginning, printed writing. Okay, so we should have log of. So this is the answer. This is the answer. So from here, we should have logarithm of, again, what is the base? It should be the same base as the exponential function. So base is 2. It takes the output. So it takes the output, which is 8, and it should return us the input. So it should return us the input. So we read this as logarithm of 8 to the base of 2 is equal 3. Alternatively, you can say, look, you can say 2 to the power of 3 gives me 8. Or in other words, 2 cube is 8. You see, 2 cube is 8. So it's like they are saying the same thing. It's just different way to express this relationship. There is a relationship. Look, we have 3 values right now, 2, 3, and 8. What is the relationship between these 3 numbers? You can express that relationship in the exponential format and say 2 cube is 8, or alternatively, you can express it in the logarithmic format, which says log of 8 to the base of 2 is 3. And just keep in mind that it's just, these two are two inverse functions. So the original function is 2 to the x, and here the inverse function is log of x to the power of 2. Okay, let's look at the next one. So as you can see, 2 cube equal 8 is equivalent to log of 8 to the power of, log of 8 to 2 is 3. Now, 5 squared is 25. Let's do this. 5 squared. So the next one is 5 squared is 25. So I'm gonna do this without drawing the function and inverse. Look, so you can say this is exponential. So we can this is an exponential relationship. So we can express that as also as logarithmic expression. Now, what is the base? The base is 5. The base is 5. So that goes and sit here as the base. So whatever is the base of exponential function, that number, that value is the base of logarithmic function. Now, what is the input value? It should take the 25, just switch the input and output value. So it should take the 25 and it returns us 5. So 5 squared 25 is the same as saying logarithm of 25 to 5 is 5. Guys, you can always double check your work to see if that's correct. How? Just remember this direction. Whatever is the base, you already learned about this index, that is the base. If you go, oops, my bad. This is 2. Because here, the input is 2. You see, the input is 2. So it takes 2. So it calculates 5 squared. It returns 25. So the input is 2, not 5. Okay. Now, let's check if what we write is correct. Look, base, right, to this number, 5 to the power of 2 should give me the value that sits in front of log. So you can always go in that direction to check your work. See if that's correct. Is that correct? So what does it say? It says 5 to the 2 should give me 25. Is that correct? Yes, because 5 squared is 25. So now this is correct. Let's do another one. 10 to negative 4 is 1 over 10,000. Okay, let's look at this example. 10 to the power of negative 4 is 1 over 10,000. So look here, what it does is that it takes, so it takes negative 4, then it the exponential function takes the negative 4, calculate 10 to the power of negative 4, and it returns 1 over 10,000. Okay, so this is the input value, and this is the output value. Okay, logarithmic function is the inverse function. So now it should take the output, which is 1 over, you should, maybe I write this again. So the inverse function should take the output value and returns the input value. So it should take the output value. And what is the base, by the way? Because I need to put the base here as well. The base is 10, you see? The base is 10. It's 10 to the power of, so the base goes here, and it should return me the input value, which is negative 4. So equivalently, you can either say, so look, you can either say 10 to the power of negative 4 is 1 over 10,000, or you can say logarithm of 1 over 10,000 to the base 10 is negative 4. So this is an exponential expression that shows the relationship between these three values, and this is a logarithmic expression that shows the relationship between these three values. In terms of function, if you look at this function, which is this is 10 to the x, here you have the inverse function, which is log of x to the power of, to the base of 10. Okay, so as you can see, whenever you have an exponential function, you can express it in as logarithmic equation. Now let's do reverse. Let's do reverse. In example 2, we are given logarithmic equation. The question asks us to express the relation in exponential format. So this is example 3. Maybe I write it somewhere else. Maybe I write example 3 here. So this is example 2. Okay. So the question is, the first one is log of square root of 6 to the base of 6, right? The base is 6 is half. So the question is rewrite this in terms of exponential function. So I'm going to be quick here. This is the base, right? Recall that this is the base. So just recall what I told you in terms of checking. So you should have base to the power of this exponent. So this is your exponent. So you should have 6 to the power of half gives you this guy, which is the square root of 6. So from logarithmic expression, we went to exponential expression. So you can either say log of a square root of 6 to the base 6 is half, or alternatively, you can say 6 to the power of half is equal a square root of 6. the next one. Log of 9 to 3 is 2. So the next one says log of 9 to the base 3 is 2. Rewrite it as exponential function. So what does this now mean? So base is 3, again, base to the power of this exponent should give me this guy. So let's just write it. Base to the power of 2 is equal 9. Is that correct? Yes, because we know that 3 square is 9. So, okay, so I recommend you to try rewrite this exponential function as a logarithmic equation to have more practice. Now let's look for another example. So, for example, it asks us to solve this equation for x. It's a logarithmic equation. Look at this question. This is nice. Example 3. The question says, solve log of x to the power of, log of x to the base 4 equals 2. Solve this for x. In other words, what is the x value that satisfies this equation? So I don't know. I mean, at this moment, I don't know how to solve this, to answer this using log, but I know that any logarithmic equation can also be expressed as exponential expression. So let's rewrite this. So rewrite this in the format of exponential function. Look, this is base, and this is gonna be the exponent, right, in the exponential format. So go base to the power of 2 must give me this guy. So just rewrite it. So this says base to the power of 2 must give me x, right? So from logarithmic equation, we went to exponential equation. And now we can do that because we know how to calculate 4 squared. 4 squared is 16. So there we go. X is 16. Got it? So sometimes if you have an equation in the logarithmic format, you may just translate it or transform it to exponential format, and then you might be able to solve it. Now, let's do this one too. Okay, so this is our original question. Remember, look, I'm gonna show you now how to do this one. Let's go back to the example we started this section with, which is right here. Okay, so so on top of this picture, you see that we started this section with this scenario that we have suppose a population of flies or 50, and they grow every week. They become double every week, right? And then we came up with, and then the question was that at what point, when does the population reach 500? And when we reduce this question and we simplify, we reduced it to, okay, for what x value 2 to the x is 10, right? And then we said, okay, we don't have a tool to solve this equation now. For that reason, we we saw the need for an inverse function, and we introduced the inverse function. So now if you want to answer this question, that let's answer this question. For what x value? Because from the graph, you can see that the answer is a value between 3 and 4. Somewhere between 3 and 4, it gives me the 10. Again, one more time. Look here, somewhere between 3 and 4, it gives me the 10, right? This is 10. So somewhere between 3 and 4 is the answer. But what is the exact value? If you want to find the exact value, you can use the logarithmic function. So again, the question is, I'm going to rewrite it one more time. Look, the question is, solve this. Okay, I'm sorry. So the question is, solve 2 to the x equal 10 for x. For what x value you have this? I don't know, but I can now use logarithmic function, which says, okay, so this reduced to log of, what is the base? The base is 2. So the question, because what is the logarithm of 10 to the base of 2? That is going to be the answer. So the answer, the power, the exponent that we are looking for is just logarithm of 10 to the base of 2. So if we can calculate that, then we are done. And in fact, you can do that by calculator. So let me show you. If you don't have a scientific calculator, you can go to GeoGebra to use the free scientific calculator. So here we want to calculate. So in this calculator, you see 2 logarithm notation. If you click on this one, that gives you, that has a fixed base. You see the base is 10. You see that? But if you click on the other one, you can choose the base that you're looking for. And I'm going to show you example of both. But in this question, what is the base? Base is 2. So I have to click this one because I have to enter that the base is 2. And then we are looking for logarithm of 10 with base 2. Here we go. This is the answer. And if you want, you can round it to the number. You can round it. For example, we can round it to 4 decimal, 3.3219. 3. So the x is 3.3219. So, and it makes sense because we saw that from the graph. You see, from the graph, we can see that x is a value between 3 and 4. So we estimated that it should be 3 point something, but we didn't know what is the exact value. And in some cases, we don't need the estimation, we need the exact value. And the exact value is right here. You see that? So the exact value is 3.3219 and more decimal, which we can absolutely can round it if you want. Okay, so so here is the idea of logarithmic function. I just wanted to make sure that you have an understanding that this family of function, which you commonly see them on your scientific calculator. So you see the log to the base of 10, log to any base. These are in fact just the inverse function for exponential function. But we give them a name because we are going to use them often. So we give them a name and notation to simplify the calculation. And one more thing. When the base of logarithm is 10, we call it common log. Okay, so we have, there are 2 bases that, because we use them a lot, we give them a name, and even you can see them in your calculator. So if the base is 10, we call it common log, and we often don't even put it there. So if you see log of x without any number, any value written as the base, that means the base is 10. So when the base is 10, typically we don't even write it. But on this scientific calculator, look, when I hit here, 10 is written to make sure that you know in this calculation, if you press this, it's gonna, the base is 10. Okay, so this one is log of x to the base of 10. It is called common log. We have one more notation for natural log. Natural log is a logarithm with base e. Just a quick reminder, what is e? So E Euler number, if you want the exact value for the E, it's 2.71828 and so on, which we roughly estimated as 2.72. So whenever you see E Euler number, that's just a notation. E is just a notation that represents this value, which is roughly 2.72, okay? But what if E is the natural log? Then we use this notation, this guy. You see ln, and we call it natural log. So natural log, what is natural log? It's the name, we give this logarithm a name. It's a name for the logarithm that has a base of e, and we typically write it as ln or natural log of x. So in this calculator, I'm gonna do it one more time. Look, in this calculator on GeoGebra, you have you can see three logarithmic function. This guy gives you ln. So this means that this is a logarithm that the base is e. Okay, so this is natural log of x, right? So and the second one is this guy. This is this is called common log because the base is 10, and the last option is this. So it doesn't put any, it gives you the option to put the base. So if, for example, you are in your calculation, you need to calculate logarithm of something in base of 3. So you put 3 here. If the base is 6, you put 6. If the base is 9, you put 9, and so on, okay? So you need to know how to, when to use each one of these logarithmic functions. But yes, since we often use a logarithm with base e or a logarithm with base e, so we gave these two functions a name, and we use this notation to represent them. So for example, when the question says evaluate log of 10,000, so this is example 5. So the question says calculate calculate log of, I think it was 1,000, right? Log of 1,000. So you may say, what is base? What is the base? I don't see a number. When you don't see a number, that means the base is 10. So just for the beginning, because this is just the beginning, I'm gonna rewrite this and put 10 here to remind you that the base is 10. So now the question is solve this. Solve it. What is the logarithm of 1,000 to the base of 10? So let's think that what does this mean in terms of exponential function? So it means that the base, let's rewrite this in terms of an exponential function. It means that whatever is the answer, base to that answer, to the power of that number, should give me 1,000. So let's rewrite it. So the base, which is 10, to the power of whatever is that number, question mark, should give me 1,000. So let me see. 10 square, let's guess what should be this exponent. 10 to the power of 1 is 10. 10 to power of 2, 10 square is 100. But 10 cube, look, 10 cube give me 1,000. So I think the answer is 3. How did I get the answer? so that is 3. I just rewrote this logarithmic expression as exponential function, and because this was easy to guess, we came up with the answer that okay, so x must be 3 because 10 to the power of 3 or 10 cubed gives us 1000. So from this, you can see that there is one of the properties of logarithmic function. I'm going to write it here. Look, let me rewrite this expression one more time. So we have log of 1000, right? 1000 to the power of 10, which is 3, right? This is what we observe. Let's see if we can find a pattern or something here. What is 1000? 1000 is in fact 10 cube, right? To the 10, which is 10. So I just rewrote 1000 in the form of 10 cube. So you can see that it seems like you can see that it seems like we have the property that 3 this expose. So just keep this in mind, which I'm gonna get back to it later when I introduce the properties of logarithmic function. Just keep that in mind. Okay, what is the question says evaluate the natural log of square root of e. Okay, so let's do this one. This is example 6. So the question is evaluate natural log of square root of e. What's the answer? Okay, so let me see. So if I know this is the beginning, maybe you say, okay, where is the base? So for that reason, I just want to remind you that the base is e. Okay, so natural log is the same as logarithm to the base of e. Okay, so the base is e. So let's go again. If you want me to answer this on top of my head, with the techniques that we know, I cannot say that. So let's rewrite it in the form of exponential equation. What is the base? The base is e, right? So recall that base to the power of whatever is this question mark should give me the sky. So we can rewrite this as base, which is e, to the power of exponential to the power of the question mark should give me square root of e. So we can guess that because we know that e or any number to the power of half gives us the square root. So the answer is half. Okay, so it's just again going back and forth between logarithmic and exponential exponential function to see that you can also alternatively solve it in this way. Look, you could also say that this is natural log of square root of e, right? So this is going to be natural log of what is a square root. Square root is just the same base, but to the power of half, right? Okay, so what is the base? The base is e. So the question is, yeah, I think eventually we end up with the same thing, that e to what power gives us, so e to what power gives us e to the half. So the power must be half. You see? Okay. Okay, so but if we have a question like this, log of 500, then I cannot easily look at this question. I want to show you when do we need to use a calculator and we cannot just come up with the answer. So this is example 7. The question is evaluate the log of 500, right? That's the question. So if I just, what is the base? Base is 10. When it's not written, it's 10. So let's see if I can answer this question by just going back to exponential function. So if I rewrite this as exponential relationship, then I should say 10 to this value should give me 500. 10 to the question mark should give me 500. So then the question becomes, what is the exponent? For what value? 10 to that power gives me 500. I don't know, because look, sometimes we can answer exponential function easily. For example, if instead of 500 we had 100, then the answer would be 10 squared. If it was 1000, the answer would be 10 cube. But 500, we don't know that. So this is not going to work in this case, just rewriting in terms of, you know, so it's not always easy to just rewrite a logarithmic function as exponential function and then guess, you know, guess what's going to be the power. So in that case, we need to use calculator. Okay, so let's calculate it. Let's use our scientific calculator. So in this case, we need the base is 10, and we need to find the log of 500. There we go. That's the answer. And depends on, usually in your textbook, sorry, in your homework or exam, it tells you to how many decimal to round it. So let me round this to 2 decimals. So it's going to be 2.6970, 2.70. So the answer is going to be almost 2.70. Okay, so if if it's not something straightforward, then we use the calculator. So now let's look at some of the properties of logarithmic function, because it's going to help us when we solve equations. So for example, one of the properties that when you have, I think you already saw it. Look, you already saw that property in some of the example. For example, look at, yeah, look at here. What do you see here? What do you see? Look, here I see that I have the input for my logarithmic function is 10q, right? And the base is also 10. So what I have here is that I have a base for logarithmic function, which is 10. And then the input value is also exponential and has the same base. You see what I'm saying? Look. So I have a logarithm to some base, and the input value is the same base to some exponent, whatever is that exponent, right? To some number. Maybe I don't use x. To some number, right? Like 3. And then what is the answer? The answer is 3. So another example. Look at this one. Look at this one. Here we have log of, what is base? Base is e. And inside also we have e to the power of half. So what we have is that this base, which is e, is the same as the base of the input value. And then the power is half, the answer is also half. So do you see the pattern? The pattern is that if you have log of, if you have, so in this case, if you have, based on this observation, I'm going to conclude this. If you have log of some base b to some exponent, let's say x, the answer is going to be x, okay? And in fact, this comes, you know, where does this come from? It comes from, this conclusion comes from this property that the power can come and sit as the multiplier of the logarithmic function. So I'm going to put that property here. Look, so this is a property. If you have a logarithm of some base, whatever is the base, and then here you have exponential functions such as b to the power of whatever, then it's this x or r or whatever is that can come and sit as a multiplier of logarithm of b to the same base. So the point is that in this property, if the input value, this is the input, so this b to the x is the input of logarithmic function. If that's in the form of exponential, that exponent, this exponent, can come and sit as a multiplier. You see? Multiplier. So you can do that. So in logarithmic function, the property is that if the input of a logarithmic function contains exponential, then that exponent can also sit as a multiplier. For example, let me show you a couple of examples. Use that property to rewrite log of 25 to the power of, wait, let me write it. This is example 8. So this is example 8, okay? And the question is log of 25 base 3. And the question is just rewrite it using exponent property for the log. Okay, what does it mean? We know that 25, right, can be written as 5 square, right? 5 square. So that property tells us that. Okay, now what is the role of these two? It's an exponent. It can come and sit as multiplier. So I can have 2 times log of 5 to the base 3, okay? So they are equal. In other words, you can say log of 5 square to the base 3 or 2 times log of 5 to 3. So that's the way to, so they hold this property, and that's a way to simplify log function. Now, let's do another one, example 9. Rewrite 5 ln of x. So now I'm gonna show you example 9. So here we have 5 natural log of x, right? 5 times natural log of x. So look, what is this 4 here? 4 multiplied by natural log of x. So here, what is the role of 4? It's a multiplier. Okay, by this property, I know that this can alternatively go and sit as an exponent of the input value. So alternatively, we can write this as natural log of x to the power of 4. You see? So it's two equivalent way to express the same thing. So now it sits as the exponent. Okay. Okay, so now another property is that, by the way, you can read the proof of these properties from your textbook, but for the sake of time, I'm not gonna go over the proof, but you can definitely go over the proof. Another property is that when you have log of, if you have a division, if you have a, so Let me see if I can explain that in a question. For a question like this, log of 10 to 2, if you just want to evaluate log of 10 to the base of 2, I would recommend just going to the calculator. So you want to evaluate log of base is 2 and the input is 10, right? So you can definitely use the calculator. I don't bother to do, you see, and the answer is roughly 3.3219. You can evaluate that, 3.3219. So for a question like that, I would say use the calculator. But for this one, yes, we can express it. Like, for example, so this property says that you can change the base. Look, the property says that you can change the base. For example, you want to calculate log of A to the base of B, right? So you can change it to another base, and then this equation gives you the relationship. So log of A to the base of B is the same as log of A to another base divided by log of B to another base, but that base should be common. For example, look at this one. We have log of 100 to the base of 5, right? So if you can alternatively write this, for example, let's say I want to use log to the base of 10, right? The common log. Okay, then you can rewrite this as a quotient of log of the input value 100 to the base 10 over log of 5 to the 10. However, I think at this, I mean, now we all have access to scientific calculators. So even if you want to evaluate that, you don't have to use that property. You can simply say, I need base to evaluate log of 100 to the base 10, and then the calculator gives you that. So I think, yeah, you should be fine for that. But the thing we need to, the things that we need to make sure we can do is solving equations that contains exponential function. Recall the original scenario, the original discussion of this lesson. Look, let's go back to the original discussion. What was it? The question was that we have a model, we have a scenario, and we have a model. That models, recall, that models predict the population of flies, right? So this was the original question that, okay, this function f of x 50 times 2 to the power of x models the population of flies. And we want to predict that after like how many weeks or how much time, then we reach a certain number in our population. So in questions like this or in scenarios like this, we need to solve equations that contains exponential expression. So don't forget the goal of this lesson, that we need to, we introduced logarithmic function, we went over the properties, but the goal is to solve something like this. So at the end of the day, you should be able to apply logarithmic function in order to solve a question like this. So for example, so I'm going to show you example 14 now, okay? Let's look at example 14. Example 14. So the question is solve this equation 5 times. And then we have this exponent term. The base is 1.07, sorry, 1.07. The power is 3t equal to. So look at this. This is an equation, and we need to solve it for the unknown variable, which is t. But the old algebra that the algebra that we know, it's not going to help, because what is the role of this unknown? It's an exponent, you see? It's an exponent. So recall that whenever the unknown variable sits as an exponent into an equation, we need to use logarithmic function. Without logarithmic function, we would not be able to answer a question like this. Okay, so let's see the solution for this question. So I'm gonna start by let's say a little simplify, because okay, let's see. How can the first step is to see that the variable is exponent, and then come up with the idea that we need to use logarithmic function. Okay, but then what to do? What's the next step? The next step is that we need to have that exponent factor. We need to isolate that exponent factor. This is the exponent factor, right? What is the exponent factor? It has a base, it has a power. That term needs to be isolated, meaning that we should have it by itself on one side of the equation. Here, I see that it is multiplied by 5. No, let's get rid of this 5. Let's divide both sides by 5. So in this way, we would have it by itself on one side. So we are going to have 1.07 to the power of 3t equal 2/5, because we needed to divide both sides, by 5. Okay, now that we isolated, we can take a logarithm from both sides. Okay, so the first step is just isolate the exponential factor to have it by itself on one side of the equation. Now at this step, take a logarithm of both sides. So I'm gonna take a logarithm, and you can do it on any base. I'm gonna do it, I'm gonna take common log base 10, but in fact, you can do it on any base, it doesn't matter. So I'm gonna take a log of both sides of this equation. So I'm gonna take a log of 1.07 to power of 3 equal log of 2/5. So the next step is what? Take log from both sides. Okay. Then the next step is, you know that we have this property that exponent, this is exponent. If you have the exponent in this place, it can come and sit as the multiplier. Recall that property? So instead of saying that log of base to the power of 3t, I can rewrite it as multiplier 3t times the rest, times log of 1.07 log of 2/5. Okay, so here I used property, one of the property of log function, that exponent, if you have an exponent as an if you have exponent as into the input of the logarithmic function, you can replace, you can switch that exponent and change its rule as a multiplier. Okay, so very good. Now t is no longer exponent. You see, that's nice, that's nice. Now my variable is no longer exponent, so now I can do the old algebra that we know. You see, it sits on the ground, so I can do the old algebra. So let's isolate 3t by itself. So I'm gonna have the 3t on one side. How can I isolate it? How can I isolate the 3t by itself? It is multiplied by this guy. So divide both sides by this guy. Divide both sides. You see what I'm saying? Divide both sides because we want to isolate it, right? So or maybe if you don't, maybe we go further at this point. Maybe wait before dividing, you can from here you can do algebra in any way that you like. But since I want to make it easier for you, maybe at this step, because look, what is the base here? It's 10, right? So you have the calculator, so you can calculate them. Let's calculate them. Let's evaluate them. So this is the first one is gonna be log of 1.04, right? So it's gonna be, let's run this. Okay, let's run this. Run it to how many decimal? Let me see how many decimal your textbook rounded. Your textbook rounded to 4 decimal. Okay, I'm gonna round it to 4 decimal. So it's gonna be 0.294. Okay. So this is gonna be 0.294 roughly. And we have the 3t here as well, right? So I just evaluated this log, and now evaluate log of 2/5. Okay, log of, here I'm gonna have 2/5. So it's gonna be, let's run this to 4 decimal, 3979, negative 0.3979. So it's gonna be negative 0.3979. Okay, so now you know the rest. You know how to solve this, because this is like a similar equation that you always had. Divide both sides. So 3t is gonna be this value divided by this value, right? Which you can use a calculator. So 0.3979 divided by 0.0294. 13, so it's gonna be negative 13 5340. Okay, and the last step is just divide both sides by 3 because we want to solve it for t, right? So, and t is multiplied by 3. So divide by 3, divide by 3, divide both sides by 3. So it's gonna be this value divided by 3. Divide by 3, 4.5113. It's gonna be 4.5113. Is that right? Almost. Negative 4.5. I carry the negative sign. I just do the calculation. Okay, fine. Yes. So that's it. So we, and recall that because we rounded to 4 decimal, this is not the exact value because we rounded that. So it's almost negative. So t is almost negative 4.5113. So depends on the rounding. Maybe you, let's see what is the value in your textbook. Yeah. Negative 4.51. Yeah. You see, this is 143. Yeah, it's because of the rounding, but don't worry about that. You got the idea, right? The idea is that if you're off 1 or 2 decimal, that's okay. The idea is that how to solve equations like this. I want to go over the steps one more time. How did we solve the equation? We first said we need to isolate the exponential factor. So we divided both sides by 5 to isolate it. Then we use the property of the logarithmic function that if you have exponent into the input of logarithmic function, that can come and sit in front of the log function as a multiplier, right? So it comes and sit as a multiplier. And then the rest was just use the calculator to evaluate the logs. And oh, by the way, did I say that take the log? Oh, I forgot one step. So the first, let's go over it again one more time. The first step was isolate the exponential fraction. The second step was take a logarithm of both sides of the function. The third step was we used property to put the exponent, to change the rule of the exponent. We move the exponent to be a multiplier of this function. And in the next step, we start evaluating and simplifying and doing some algebra to solve it for your variable. If you read the steps from your textbook carries this log of 1.04 throughout the entire, carries both of the log through the entire process. At the end of this calculation, it goes to the scientific calculator in order to do the calculation. Either way is fine. We are just off maybe few points in the decimal, and that's because of the rounding, but we are pretty close. Okay, so that's it. I recommend you to read and go over the couple of more examples in this section. So we went over almost important properties of log function. I think you should be now ready to do the exercises of this section. Thank you for watching this video. I'll see you in the next one.